Great. Welcome, everybody, to the last TAPIRS talk of the term. We're delighted to have Phil Tosteson here today to tell us about Koszul complexes and FSop modules.
Awesome. Yeah, thanks so much for having me. It's nice to be kind of virtually in Michigan and in a lot of other places too, I guess. So what I'm going to be talking about is, well, this is the representation stability seminar, so I can go through this kind of quickly. So I'm going to be talking about combinatorial categories, and I don't mean anything particularly specific by what a combinatorial category is. Here I have kind of listed some representative examples. So the category of finite sets and injections, the category of finite dimensional vector spaces over a field in injections, the same version but with split injections, and then C being the category of finite sets and surjections op. These are kind of like, when I say like C be a combinatorial category, I'm kind of thinking of these as being my representative examples. Though of course there's certainly other ones, just any category of a combinatorial nature. And then a C module given a combinatorial category is just a functor from C to mod K, where K is some commutative base ring. And I've written out my notation here for what this functor looks like. So it assigns a value to each object and a morphism to each morphism. And kind of the key definition that we think about in representation stability is the notion of a finitely generated module. So a module M is finitely generated if there's a finite list of elements that generate it under the action of transition maps and also taking linear combinations. Okay. And in kind of our representative examples, all of the isomorphism classes of objects are kind of listed by natural numbers. And I'm going to be slightly abusive throughout this talk, and I'm going to kind of say like, I'm going to identify natural numbers with objects when there's kind of a reasonable way of doing so. I won't do this all the time, just occasionally, and I'm letting you know in advance. But in our examples, we have the isomorphism classes are given by natural numbers, and so we have a sequence of group representations, Mn for each Gn, where Gn is the automorphism group of the nth object. And kind of the fundamental kind of algebraic question that we ask in representation stability is, given a finitely generated module over a combinatorial category, like what does that actually say? What does the fact that it's finitely generated imply about the sequence of representations Mn for n and n? And of course, the main example that we should have in mind is Fi modules in characteristic 0, which were studied by Church, Ellenberg, and Farb, and kind of in a different context by Sam Snowden. And in that case, there's this very nice pattern called representation stability, which in particular tells you kind of what happens to the underlying sequence of S-fine representations. And kind of visually it looks like this. And of course, since this work on Fi modules, there's been many other results for different categories, VI, VIC, FIG modules, type B Fi modules, FID, things in positive characteristic as opposed to characteristic 0, categories of Fi type, things like that. But I really want to kind of focus in on a specific class of kind of results, which are results on dimensions. So the simplest invariant of the sequence of representations is its sequence of dimensions. To talk about this, I need to assume that K is a field. So assume that K is a field, and then we can package the sequence dim n into a function, a generating function called the Hilbert series, where I just sum over all natural numbers of dim mn times t to the n, where t is a formal variable. And kind of the amazing thing is that oftentimes this generating function is rational. It's a ratio of two polynomials, and also the denominator has a specific form. And we can kind of rephrase a lot of our results, our favorite results in representation stability, in terms of rationality of generating functions. So kind of the classic example is C equals Fi, and in that case, HM, the Hilbert series, is rational, and its denominator is 1 minus t to the d. And this is just saying that this is just another way of saying that dim mn is eventually a polynomial. It eventually agrees with a polynomial of degree d. And when C is VIFQ, Nagpal showed in non-describing characteristic that HM of t is rational with denominator product from j equals 0 to d minus 1, 1 minus q to the jt. So this is just saying that dim mn is eventually given by a q polynomial. So a polynomial in powers of q. And then for C, the category of FSop modules, Sam and Snowden showed that HM of t is rational with denominator a power of this polynomial. Where our product, again, from j equals 0 to d minus 1, but now my coefficient is j instead of q to the j. Okay. And kind of the most general technique for proving what I would call a rationality theorem, like the theorem that says the Hilbert series is rational, is Sam Snowden Grobner theory. And that'll show that a large class of categories that you have rational Hilbert series. And it's very powerful and effective, but the main drawback is that Grobner theory kind of by its very nature involves kind of breaking symmetry. So what that ends up implying is that it only tells you about the dimension sequence. It doesn't tell you really about like the underlying sequence of representations. So kind of what I want to talk about today is I want to kind of introduce a construction, which is like the Koszul complex in the title, which kind of helps to unify these results on denominators, and also gives at least a strategy for proving kind of equivariant versions. And really, I'll be mostly talking about the case of C equals FSop, and kind of how the story works in that case. Okay, and I guess before I move on, I want to just mention one other thing, which is because this is a talk about representability, I should probably mention configuration space if there's a way of doing so. And so the Poincare polynomial of configuration space in the plane was computed by Arnold, and you can see it bears a strange resemblance to this denominator here, and it turns out that that's actually not a coincidence. You can imagine it would be a coincidence because this is not the most special polynomial. It's just you're multiplying it by a factor with j for each natural number j from 0 through d. So it's not that special a polynomial, but it turns out that this coincidence is actually not a coincidence. So to kind of describe why it's not a coincidence, I need to talk about posets. So the other way that this was first computed by Arnold, but Bresky, McPherson, and actually probably people before them for hyperplane arrangements, interpret this polynomial in terms of posets and poset homology. So it turns out that posets are kind of like what's secretly governing these denominators, and also this Poincare polynomial. Okay, so what is a poset? I'm not gonna say the formal definition of a poset, but a poset for us, we can think of it as being kind of a special type of category. So given a locally finite poset, we can consider P to be a category. The objects are just the elements of P, and a morphism, you have a morphism from P to Q if and only if P is less than or equal to Q. And then what I've written down here, a definition of it is kind of the fundamental, like the most basic invariant, combinatorial invariant of a poset, which is its Mobius function. And so the Mobius function is a function from the poset to the integers, and it's the unique function that satisfies this identity. So it's the unique function of values on elements of the poset, which satisfies this identity. I should note that usually we assign the Mobius function to intervals in the poset, because what I'm going to do is I'm just going to assume that all of our posets have a top element, 1 hat, and then I'm just going to kind of think about mu1 hat, mu p1 hat instead of the usual mu p. And it's not hard to see that this kind of uniquely determines it. So you can do it in kind of this example. So I'm drawing the Mobius function in purple. So this is the top element, so mu p has to be 1. And then That means here it has to be -1, -1, -1, so that I cancel out the 1 above and get 0, and then here it has to be 2. And there's this nice theorem due to Hall, which gives a formula for the Mobius function as an alternating sum over the number of chains. So I don't need to define it by this property. I can also just kind of write it as the alternating sum of the number of length I chains in the poset. Okay, so what I'm going to do is I'm going to tell you how to build a polynomial out of the Mobius function of a poset. So to do it, we need P not just to be a poset, but it needs to be graded. What it means for P to be graded is just that between any two elements in P, any maximal chain has the same length. So there's kind of a well-defined way of saying how far apart two elements are. So when P is graded, I'm going to define R of P to be the length of a maximal chain from P to the top element. And here, just notice that this has P plus 1 elements, but I'm saying that it has length R. So that's just kind of the normalization that I'm using. Then the Whitney polynomial, or sometimes this is called the characteristic polynomial of P, is by definition it's kind of a generating function for the poset. It's a sum over all elements of P of mu of P times T to the rank of P. And for this to exist, I probably need the poset to be finite. Or some other condition will also work, but I guess you need to have finitely many elements in each rank. Yeah, so that's the Whitney polynomial. And okay, so what does this have to do with representation stability? Well, it turns out then representation stability, if for our combinatorial categories, oftentimes the over category of an object is equivalent to a graded poset. So remember, what is the over category of an object? It's just the category that parameterizes maps to that object. So the objects are maps from X to D, and morphisms are morphisms that commute with that map. And yeah, and what happens in representability is that C over D is often equivalent to a graded poset. So let me say some examples. Here are some examples. So the first example is C is the category of finite sets and injections, and then injections to a fixed set is actually equivalent to the poset of subsets of X in containment. And the Whitney polynomial of this poset is 1 minus T to the X, to the size of X, which you can also kind of expand out using the binomial theorem. And then the second example is when C is VIFQ, and then this is just the poset of subspaces of my space W. And the Whitney polynomial again has this nice factorization, and this is kind of a version of the Q binomial theorem. And in the third case, it is the case of FSop. And in the case of FSop, the poset that you get is the poset of set partitions of X, ordered by refinement. And the Whitney polynomial is exactly the product from j equals 0 to the size of X minus 1 of 1 minus jt. So obviously this is kind of suggestive, the fact that like that from these Whitney polynomials we're actually kind of getting these denominators of getting these denominators that had been obtained for the Hilbert series, and so you kind of want to find an explanation for this. I should mention that when C is the category of VIC, you do get a poset. You get the poset of subspaces and splittings, which was kind of implicitly introduced by Charney. At least she considered the building for this poset. I actually don't know what the Whitney polynomial is. Maybe someone can tell me. It should be computable, but I haven't actually worked it out. So question mark. Okay, so we have this kind of connection that we're seeing between the denominators in Hilbert series and Whitney polynomials, and kind of the construction I want to talk about is kind of an explanation of this, a way of kind of saying like why is this happening. So I'm just going to kind of describe the main construction when C is one of the categories above. So by that I mean VI, FI, VIC, or FSop, and also in other cases too. But we'll just restrict to these cases for now. And suppose that D is a natural number. So I'm doing this thing where I'm identifying natural numbers with objects of the category, and I'm letting C over D be equivalent to a poset P. The main construction I want to talk about is a way of building a complex, a chain complex, KD of M, for every C module. And what this complex will look like is it looks like it looks like what I've written down here. So it's a homologically graded complex. So this will be in homological degree 0. This is homological degree 1. This is homological degree D. And in degree 0, it's just the d-fold shift of M. So by that I mean in each of these cases there's a module that's naturally defined kind of like this, really more formally using the monoidal structure of C. So the complex KDM that I want to talk about how to construct takes this form. Okay, so that's the 0th term, and then the first term is the sum over all P that have rank 1 of sigma D minus 1 M to the mu of P, and kind of you continue on like this. Okay, and kind of the main proposition, or the proposition that motivates this construction, is just that if KD of M is exact, at least in all degrees sufficiently large, then the Hilbert series is rational and its denominator is WP of T. So let me just show you how to prove this proposition. So it's pretty straightforward. So if we write WP of T as the sum of Ci times T to the negative I, then by definition, if we look in degree M equals N plus D, then this Koszul complex in that degree takes this form, just by definition, because the Whitney polynomial is the sum over Mobius numbers, and so is the complex, at least as I've described it. It's also a sum over Mobius numbers, or a sum over elements to poset to the power of the Mobius number. So it looks like this. So we have a complex that looks like this, and if this complex is exact for n sufficiently large, then the alternating sum of the dimensions is exact. So we get this equation. If we add up this equation times t to the n, then we see that WP of t times HM of t is equal to this quantity, which is 0, which is 0 for all n sufficiently large, which means that this is a polynomial. Means that this is a polynomial f of t, and then you can just divide by WP of t to get that you have a rational function. Okay, yeah. So that's kind of why like these complexes are kind of an interesting thing to consider if you can kind of construct a complex like this. So the idea is that the exactness of this of KD of M categorifies kind of rationality of the Hilbert series. And I'm not going to tell you the theorem. I'm just going to tell you kind of a form of a theorem, and then I'll tell you specifically what happens for FSop, which is kind of the most interesting case. But the Proto Theorem is that let C be one of these categories, Fi, Vi, Q, or FSop, and let M be a finitely generated C module. Then there's some S and some D, such that if you apply KD S times, then you get something that's exact in high degree. So what that Proto Theorem is saying is basically that like it's a way of categorifying the fact that like it's a way of categorifying that HM of T has denominator WP of T. Yes. Okay. But before I kind of tell you about this, I've just told you roughly what the complex KD of M looks like, and I want to tell you actually how to construct it. And then kind of give you some examples of what it looks like a little bit more concretely in different cases. Okay, so here's kind of the more formal aspect of how you actually construct this complex. So the setup is, suppose that CO+ is a monoidal category, and suppose that we have some object D in C such that C over D is equivalent to a poset. Then the monoidal structure means that we can get a functor from C times C over D to C, which is just exactly what you think it is. It's just summing using the monoidal structure. And what this does is it induces a functor by restriction from C modules to mod C times C over D. So then the idea is that so we have a functor from C modules to this category, and if we choose some functor f from mod C over D to chain complexes, then I can apply f in the second factor. So I can apply the f in this factor here, and then compose with f to get a functor from mod C to chain complexes in C modules. So if this sounds a little bit complicated, I can just say what that is a little bit more concretely. So if we have this functor f, then like f compose reso plus is just the module C maps to f of m direction C plus. So it's like we take our module and we think about it as a module over a thing that's equivalent to a poset, and then we apply some functor from posets to chain complexes. And then really, like, what I have to say is what is f? So like what functor from poset modules to chain complexes do we choose? And it turns out there's a very natural choice, which is given by doing what I would call poset homology with coefficients, which I believe was first introduced by Baklowski, but I don't know the history well enough to be absolutely sure. So let P be a poset with top element 1 hat, and let M be a P module. Then we can define BP of M to be the following bar complex. So as it's a bar complex, it's a direct sum over chains of elements in P of M of the value of M at the last element PS. And the way you define the differential, as kind of often works with these bar complexes, is an alternating sum over delta I. And what delta I does is, if I equals 0, it's just 0. I guess I didn't even have to write it in my sum, but it's kind of helps me to know that it's there anyways. And then if it's some number between 1 and s minus 1, then you just forget. So if it's equal to I, then you just forget the ith element. And if it's the last one, then you forget the last element, and then you also apply the transition map MPS minus 1 to MPS. Okay, so this is just kind of an explicit bar complex. And you can kind of see that if you know something about order complexes and poset topology, that BPM is closely related to the order complex, which I'll denote by NP. So this is just I won't define it out completely, but it's just a complex whose simplices are chains of elements of P. Okay, so this is kind of the bar complex, and it always exists if you have a poset with a top element. But it turns out that when your poset is very combinatorially special, like when it satisfies a certain connectivity condition, then you can replace it by a much smaller chain complex, which is nicer. So let me go to here. Okay, so what I have here is a definition. So when P is graded, and also the order complex of the interval, the open interval, which is the nerve of the open interval from P to 1 hat, is sufficiently connected for all P and P, then we can actually define a smaller complex sitting inside of BP, which has the same homology. So this complex KP, what it is it's just you only consider it as it's a submodule of all the chains that kind of are saturated, have maximal length. So that this condition here, RPS equals S, says that this chain doesn't really have any gaps in it. And then you don't just consider this module, but you consider the kernel of all the operators except for the last one on that. And it turns out that this is a subcomplex. And if you think about kind of what the definition, so maybe I shouldn't have said by definition, that's a little bit too bold here. But it's actually not so, it's not so bad if you've kind of worked with these order complexes before, to see that KPMS is really the reduced homology of this nerver, this order complex with coefficients in P. And furthermore, by Hall's theorem, you can see that because we've assumed this connectivity, that like the rank of this group is actually given by an Euler characteristic, which is an alternating sum over chains, And so you can see that actually you can write it like this. Yeah, does anyone have any questions about this complex? So if not, then what I have here is that KPMM to BP of M induces an isomorphism on homology. And the way you prove this is just by filtering BP of M. So you can filter BP of M kind of, the module M actually comes with a natural filtration just by the rank. You can like look at the submodule spanned by the elements of rank less than or equal to something, and that gives you a filtration. And if you look at the associated graded, then you get a spectral sequence which degenerates because of this connectivity condition. And so you can kind of just do the comparison like that. You can probably also just say it directly without using the word spectral sequence.
Can I ask quickly?
Yeah.
Is this complex computing in the FI case? Is it FI homology?
You can compute FI homology with the complex, but right now I'm just in the setting of a coset. So you can use this complex in the FI case to compute FI homology. I'll say more on the connection between what I'm doing in like module homology in a little bit. So I just want to do a little example, which is, you can do the third partition poset, which looks like this, which is what we get in the FSop case, and you can compute out what BP 3 of M is, and you have a term here for each of the length 2 chains, and then there's 3 length 3 chains. So you have 3 basis vectors here, and then you need to choose some sort of basis for the kernel to compute the second line. Kind of the kernel in both these cases is trivial. The kernel here is spanned by the difference of any pair of chains. So you can choose 2 chains and you can choose 2 of those differences, and that'll give you this here. So this is kind of what it looks like in the P3 case. So I'll briefly mention that there are like fancier ways of thinking about what BP and KP are and are doing. So the first off is that since it's a bar complex, you can compute it. You can interpret it as being a certain Tor. It's a Tor with, so you can take the Tor, you can take the tensor product of a P representation and a P op representation, which is that if you compute Tor with this P op representation, then you get the complex BP. One perspective that's a little bit more topologically suggestive is you can think of BPM as being the cone of the homocopy colimit over all elements P less than the top element, MP mapping to M1. So it's kind of, what it's doing is it's measuring the difference between M1 hat and kind of everything below it. This is kind of like the free approximation of all the things below it. And the third thing is that like you can interpret KP of M as being a Koszul complex in the sense of Koszul probability theory. So there's a theory of kind of simplifying bar complexes into smaller ones that sometimes works, and this is kind of an instance of it. Okay, so what's the point here? So if we go back to our function f and we take f to be either BC over D or KC over D, then we obtain functors BD and KD for mod C to chain complexes over mod C. So KD is defined in the following instances. So it turns out that many cosets have been checked to satisfy this connectivity hypothesis. In particular, any Cohen-Macaulay coset satisfies the connectivity hypothesis, and so KD is well defined. And so it's defined in kind of all of these cases because kind of the categories we study in representation stability are so combinatorially natural. Somehow everything works out very nicely for them. Okay, so let me do some examples. So to kind of Neer's question, the reason why this is slightly different from FI module homology is because of the fact that we kind of restricted along this symmetric monoidal product. So when C is equal to Fi, this complex can be kind of familiar. It takes this form. It's the complex that you get by considering the map from M to the map from M to sigma of M, and taking the cone D times. So it's kind of, as opposed to like an FI module homology complex, it's going to be just a finite complex, but it's closely related to FI module homology. When C is VIL, then these poset homology groups that I was describing K in terms of earlier, they're exactly the groups that give you the Steinberg representation. So you have this nice description. So you have this nice description where you have sigma W of M, and then you have a sum over all codimension 1 things, and all over codimension 2 things tensor the Steinberg representation of W mod V, and it kind of continues like that. So you get Steinberg modules. And then when C is FSop, it starts the same, and now you're kind of direct summing here over all partitions of D of the set D. So D is my notation for the set with D elements into, these are all codimension 1 partitions, which are just given by choosing a pair of 2 elements to identify. And it turns out that the function you get is just the Stirling number of the first time. Okay, so those are kind of the three main examples, and then I'll mention just one other example, which kind of explains why I might call this a Koszul complex. So this is for C, this category. So I haven't actually told you how this category works, but this is the category that's really just defined in such a way such that C modules are the same as graded K joint XY modules. So the grading is given by like an object, and then you have a map from I to I plus 1. You've got X and Y, and you can compute that KD of M is just the Koszul complex, or it's a Koszul complex with a shift. So this D means that I have to shift. Okay, so that's these examples, and then I should mention kind of one interpretation of KD slash BD, which is in terms of C module homology. So this kind of goes more specifically to Neer's question. So what it says is that if C is an EI category, then there's a natural notion of C module homology, which is really just, you take the definition of FI module homology and you modify it in the way that you think you will, and you get C module homology. And it turns out that what BD or KD computes is it computes the functor where you first restrict to C times C modules along the symmetric monoidal functor, and then you apply D module homology. You apply C module homology. So this is HIC blank in degree D. so this is a way of kind of interpreting these complexes in terms of C-module homology, though it turns out that the kind of the interpretation in terms of post-set representations is more convenient for actually kind of proving things about them. Okay, so that yeah, so that's everything I had to say about kind of the general case, and now I kind of want to talk a little bit more specifically about what happens for FSop modules. So what happens for FSop modules? So let me just give you some quick background on FSop modules, which I won't go too much into, but they're proved Noetherian by Sam and Snowden, and they were used to prove the Land-Schwartz-Artinian conjecture. And in the past, they've been applied to. They were first applied to the Kasdan-Lustig polynomials of braid matroids. And then I applied them to the homology of the moduli space of stable curves. And in joint work with Peterson, we apply them to the homology of Kontsevich mapping spaces. And recently, Proudfoot and Ramos connected them to resonance arrangements. And kind of the general philosophy is that things that are kind of naturally Fi modules in algebraic geometry, their compactifications are often naturally FSop modules. And there's kind of a surprising analogy and connection, which is joint with Sam Snowden between Fi modules and the polynomial ring in one variable and FSop modules in a certain Lie algebra, the Lie algebra of formal vector fields on the unit disk. But it turns out, in general, FSop modules are just they're not as well understood, partly because this object is a lot harder than this one. So just to give you an example of what sort of phenomena you can expect to get from an FSop module, I'm going to tell you about a specific FSop module. And this is an FSop module that you can get by linearizing an FSop set. So this is the module that assigns to X the free vector space on all set partitions of X into two blocks, where the blocks are not ordered. This M is naturally an FSop module because if you have a partition P of X into two blocks, then you can always just partition Y according to which thing it gets mapped to under F. So by pulling back the partition, you can show that M is an FSop module. In fact, it's a projective FSop module. But we won't need that. And it is generated in degree less than or equal to 2. So there's two generators. The two generators are this partition and this partition. So there's a generator in degree 1 and a generator in degree 2. And the trace. So say I want to compute the character of this SN representation or this aught X representation. So if I have a permutation sigma of X, the trace of sigma is the number of partitions which are fixed by sigma. So here I'm thinking of sigma as being a permutation X to X. So it turns out that there's two cases. So if sigma has a cycle of odd length, then sigma has to fix each block. Like it can't map one block to the other block because you can't do that with your odd cycle. And so you can count the number. So this has a cycle of odd length that has to fix each block, and then for each cycle in sigma, it turns out that for each cycle in sigma, it has to either be contained in its orbit. It has to either be contained in one block or in the other block. So you can compute this trace. And here xi sigma is the function, which is by definition the number of I cycles of sigma. So this function xi of sigma is kind of a way, at least for Fi modules, that it's common to kind of describe SN characters. So I want to describe a function on, I want to try to describe a function, and I'm doing it kind of using this function xi of sigma. Okay, but the thing that's tricky is that if all the cycles have even length, then there's a different formula. So if all the cycles have even length, then you actually get the trace is actually twice as large. And the reason why is because there's two ways you can preserve the set partition. Now you can either preserve each block individually, or you can kind of interchange the blocks. So there's two terms, and so you see that there's kind of things happening that can't happen for FI modules. So I'll just recall verbally that for FI modules, the SN representations that you get are simply like polynomials in these xi's. And here we're not getting a polynomial, we're getting like an exponential. And not only is it exponential, it's all of the terms are showing up. So it's like x1 plus x2 plus x3, so on to infinity. And furthermore, like there's some sort of congruence thing happening where there's some sort of parity. So this is the way in which FSop modules can be harder, even for the simplest case, which is the projective modules. Okay. So that's kind of what FSop modules look like, and now I want to tell you about what I proved, like what my Proto Theorem looks like in this FSop module case. So what it says is that let M be an FSop module, which is a submodule of one that's generated in degree D. Then there's an S such that for all tuples of S elements in N, such that each Li is bigger than D, then this chain complex is exact. So it says that, so maybe I should clarify, can iterate KD of M by taking the total complex. I'll call it KL of M here. So as I've defined it, KL takes as input an FSop module and it outputs a chain complex. But you can also input a chain complex to KL, and you'll get out a bicomplex, and then you just take the total complex. So it makes sense to form this iteration, and you can ask whether it's exact, or you can try and prove that it's exact. And basically, I'm not saying much about how to actually prove this, but the key ingredient is to use Samson and Grabner theorem. And taking Frobenius characters, it turns out that this equation here will translate into a system of linear differential equations for the character of M. So each of these complexes, somehow you can interpret it as a differential operator or as a sum of differential operators. And the fact that this is exact means that that set of different differential operators annihilates the character of M. And then you can just try and solve the system of linear differential equations. And that'll tell you something about the characters. So I'm gonna tell you what this says about the characters. But to do so, I need to talk about character exponentials. So what is a character exponential? So if A is an integer partition, like 1 to the A1 to the A2, and here that's just, this notation here is just telling you how many parts that partition has that have size 1, how many parts it has that have size 2, and so on and so forth. So I've kind of drawn here what A1 and A2 represent in terms of the Young diagram of the partition. Okay, so if you have an integer partition, then you can define A to the X to be the product over all N of kind of this funny sum. So it's the sum over all D divided N of D times AD X to the N. So this could be a funny thing to look at if you know symmetric functions and kind of prefer them. It corresponds to this symmetric function, where you plug this as a power sum function with the sum over all homogeneous functions. And in this definition, it's kind of really important that 0 to the 0 is 1. So when A is equal to 1 squared, or 1 squared, then what you get is you just get that A to the X is equal to the product over all N of 2 times X to the N, which is the 2 to the sum of Xn. So So you can see that this is kind of something that we were seeing before. And then when b is 2 to the 1, then you have a product over n odd of something 0 to the xn times the product over n even to the xn. And what's happening here is that this is 0 unless all the cycles of sigma are even. So you're getting kind of this parity out. And it turns out that the above example, you can describe it in terms of a character function as a to the x plus b to the x over 2. Okay. So this is kind of a character exponential, and it turns out that to describe the characters of FSop modules, I need something slightly more general, I need something slightly more general, which is this function, which I call x choose new a to the x minus new, which is a product over all n, and it corresponds to this symmetric function here, where I've just taken my symmetric function from before and multiplied it by p nu over z nu. And it again, you have to be kind of pay attention to what this actually means. But it turns out that this is always a natural number, and in this case it's non-zero if and only if sigma and s has cycle type nu. Okay, so in terms of these definitions, kind of what the first theorem I showed on characters says is that if you solve kind of these differential equations that I was referring to before, then what you get is that if so first I really need to tell you what an FSop module of type DS is. So really I should say class. And so we say an FSop module is class DS if the conditions and hypotheses of previous theorem apply to it. So what that means concretely, if I scroll up here, is just that first off, I need M to be a submodule of one that's generated in degree D, and second, I need this condition to apply for this S. Okay, and then so the theorem that I said before says that every module kind of has type DS for some choice of D and some choice of S. So if you have an FSop module of type DS, of class DS, then what I proved is that the character of M takes this form. It's a sum of x choose nu times a to the x minus nu, where A has bounded size and nu has bounded rank. So it turns out this sum is actually not a finite sum because I haven't bounded the size of nu. I've only bounded its rank. So the rank of nu, this rank of nu, is number of rows in the Young diagram of nu. Okay. So that's the first theorem. The second theorem is a finite dimensionality theorem. And for this, you need more than just the differential equations I mentioned before. You also kind of need another fact about FSop modules, but you can show that there is a finite dimensional space of class functions UDS, which contains all of the character functions of FSop modules which have class DS. And its size is given kind of by some binomial coefficient times the number of integer partitions of size less than or equal to D. And then the final result for FSop modules is an analog of kind of classical representation stability for FI modules. So here n lambda is kind of denoting an integer partition with a long growing top row. And what this theorem says is that the multiplicity of n lambda in n plus the size of lambda is eventually a quasi-polynomial of period less than or equal to d and degree less than or equal to ds. So in the case of Fi modules, you have that these multiplicities stabilize, and for FSop modules, you can only say that they're eventually quasi-polynomial. Okay, so that's what you can kind of get out of you can get out for FSop modules. And yeah, so before I end, I just want to mention a few questions which I think are interesting, which is one main question is just for which categories can you kind of prove a version of the Proto Theorem that I mentioned before? So it turns out that I know how to prove versions of it for Fi and for VIQ and also for FSop modules, but I don't really know what the right level of generality is for when does M being finitely generated mean some power of this complex KD of R, and KDM of R is exact. So I think maybe one of the most interesting cases is the case of VIQ and describing characteristic. So using the work of Nagpal, I can prove that KD of M is exact in non-describing characteristic, at least modular torsion, and at least for D sufficiently large relative to the generation degree of M, I can prove that. But in describing characteristic, I don't really know. The other big question is just, which is really important for applications, is just, let's say I have a short exact sequence of FSop modules, or just a map of FSop modules. Like, what does the class of two of them tell me about the third? So you can see that it kind of behaves well with extensions and co-kernels, but maybe not so nicely with kernels. I guess with co-kernels, it also doesn't behave. So by not behaving nicely, what I really mean is that I don't really know how to bound the class that well. It's like if you handed me a presentation for the FSop module, then I could probably do it. But kind of in applications, it'd be good to have a version of kind of theories that we have for Fi modules. And the third big question is just, what is the representation theory of FSop? It's like I can tell you all these things about its characters of FSop modules, but I can't tell you so much just about what actually is the representation theory of FSop. And the question is, can the complex KDM be used analogously to M to sigma M for Fi modules? Okay, so those are my questions. I wanted to say thanks for being here, and also thanks to Andrew and Jenny for organizing this great virtual seminar.
Let's thank Phil. Do we have questions for Phil?
Yeah, I think I had one so it's slightly unrelated, but it's about VI modules and describing characteristics. Do you know if there are any conjectured rationality results as such?
Yeah, so I think the conjecture would be that you have a, so what I would conjecture is that you have a power of like, you have a power of the denominator that you have for non-describing characteristic. I don't know who's told me to think about this way. Probably Nate, some combination of Nate and Stephen.
Wait, Stephen, did you prove that?
No, I thought I had an argument, but Phil explained to me why it's not correct.
Oh, okay.
Yeah, that answers my question. Thanks.
Anyways, yeah. So I'm in a power of this one.
So the best result known in describing characteristic just comes from what you get from thinking about it as an FSop module?
I guess, yeah.
Okay, wow.
Yeah, I guess, yeah, the problem is that just for the order, so like the way I like prove this theorem for FSop modules And the way you kind of prove your results is by using FSop. And then for VI, you have the category OVI, but it turns out that its principal modules don't have the property that you want them to have.
Yes, conceptually about these, when you iterate the complex, is there a way I can think about it to understand what does it mean if it is exact after one application or after three? I mean,
yeah. So it means like what power of the Hilbert series do you have to, like what power of the Whitney polynomial do you have to divide by in order to get the Hilbert series?
in terms of representations, does it have?
Yeah, I guess like it's like how far away is it from being projected? So like for that's what I would kind of say. So like if you had like if you have like an FSop module that's generated, it's like a submodule of one generated in degree D, but it's generated in degree D plus K, then you kind of expect to have to do it K times. I don't think I can prove that necessarily, but that's kind of the intuition.
For FI modules, even the projectors, you might have to do multiple things, right?
Yeah. Yeah, well, it depends on how you interpret it. So like for FI modules, you can say like, for FI modules, you have the K1 to the R. It's like isomorphic to KR.
Oh, okay. Yeah, I was just thinking about K1, I guess.
Yeah. Yeah, so if you can do R one times or one R times.
Do we have any more questions for the speaker? All right, let's thank Phil again. And I will stop the recording if I can figure out how to do that.